NENOMATICA, where mathematics meets YouTube excellence. Welcome to our math video. Today we're going to solve a parametric equation problem step by step. Let's start with our example. We need to solve and investigate the following parametric equation. First, let's expand the left side of the equation. We'll multiply x minus a times x plus b. This gives us x squared plus bx minus ab. Now, let's simplify the expression on the left. We can group like terms to get x squared plus b minus a times x minus ab. This step helps us see the equation more clearly. Now, let's expand the right side of the equation. We apply the square of a binomial formula to expand x minus a plus b squared. This gives us x squared plus a squared plus b squared minus 2ax plus 2xb minus 2ab. Now we'll group the like terms on both sides of the equation. We can organize this as x squared minus x squared, plus bx minus 2bx, plus negative ax plus 2ax, plus negative ab plus 2ab equals a squared plus b squared minus 2ab plus ab. Now we simplify the left side by combining like terms. The terms with x squared cancel out. For the terms with x, we have bx minus 2bx, which gives us negative bx. We also have negative ax plus 2ax, which gives us positive ax. And for the constant terms, we have negative ab plus 2ab, which gives us positive ab. So, the left side simplifies to ax minus bx. Let's factor out x from the left side. We get x times a minus b equals a squared plus b squared minus ab. Now, we can solve for x by dividing both sides by a minus b. This gives us x equals a squared plus b squared minus ab all divided by a minus b. This is our solution, but we need to check when this solution is valid. Now, we need to consider different cases for our solution. Case 1, if it is not equal to b, then our solution is valid, and x equals a squared plus b squared minus ab all divided by a minus b. Case 2, if it equals b and both are not 0, let's substitute this back into our equation. We would have x equals a squared plus a squared minus a times a all divided by a minus a. But a minus it equals 0, and we can't divide by 0, so there's no solution in this case. Case 3, let's consider what happens if a and b are both 0. In this case, our equation becomes x times 0 equals 0 squared plus 0 squared minus 0 times 0, which simplifies to 0 equals 0. This is always true for any value of x, so we have infinitely many solutions. Let's look at our example. Let's start by finding a common denominator on the left side of the equation. We need to multiply the first fraction by x minus b over x minus b, and the second fraction by x minus over x minus a. Now, let's simplify the numerator in the left fraction. We have x minus b minus x plus a, which simplifies to a minus b. Since we now have the same numerator on both sides, a minus b, we can set the denominators equal to each other. This gives us x squared minus ax minus bx plus ab equals x squared minus ab. Now, let's expand the product on the left side. We get x squared minus ax minus bx plus ab equals x squared minus ab. Let's now consider two cases. First, case 1 is not equal to b. We continue with our expanded equation from before. We have x squared minus a plus bx plus ab equals x squared minus ab. Simplifying, we get x squared minus a plus bx plus ab equals x squared minus ab. Subtracting x squared from both sides, we get negative a plus bx plus ab equals negative ab. Now, let's move all terms to the left side. We get negative a plus bx plus ab equals 0, which simplifies to negative a plus bx plus 2ab equals 0. Now we can solve for x. Dividing both sides by negative a plus b, we get x equals 2ab divided by a plus b. So, when it is not equal to b, the equation has the solution x equals 2ab divided by a plus b. Let's look at our example. We need to solve and discuss the parametric equation. M cubed minus n cubed times x equals m minus n. Our first step is to apply the difference of cubes formula to the left side. Remember, the difference of cubes can be factored as a cubed minus b cubed equals a minus b times a squared plus a times b plus b squared. So, m cubed minus n cubed can be factored as m minus n times m squared plus m times n plus n squared. Now, we'll analyze this equation by considering two cases. Case 1, if m minus n equals 0, then m equals n. In this case, our original equation becomes 0 times x equals 0, which means that x can be any value. The equation has infinitely many solutions when m equals n. Case 2, if m minus n is not equal to 0, then we can divide both sides by m minus n. This gives us m squared plus m n plus n squared times x equals 1. So to summarize our solution, when m equals n, the equation has infinitely many solutions. When m is not equal to n, the equation has exactly one solution, x equals 1 divided by m squared plus m n plus n squared. M squared x minus m squared equals 3mx minus 2x minus 1. We need to determine for which values of the parameter m this equation has solutions. Let's start by rearranging the equation to get all terms with x on the left side and all other terms on the right side. We move 3mx and negative 2x to the left side and m squared to the right side. Now, we can factor out x from the left side of the equation. We get x times the expression m squared minus 3m plus 2 equals m squared minus 1. Next, we solve for x by dividing both sides by the expression m squared minus 3m plus 2. This gives us x equals m squared minus 1 divided by the expression m squared minus 3m plus 2. Let's factorize both the numerator and denominator to simplify our expression. For the numerator, m squared minus 1 can be factorized as m minus 1 times m plus 1. For the denominator, m squared minus 3m plus 2 can be factorized as m minus 2 times m minus 1. Now we can simplify by canceling out the common factor m minus 1 from both the numerator and denominator. This gives us x equals m plus 1 divided by m minus 2. Now, we need to determine for which values of m this equation has no solution. There will be no solution when the denominator equals 0, which happens when m equals 2. When m equals 2, we get a division by 0, which is undefined. We also need to check if there are any other special cases. Let's examine what happens when m equals 1. Substituting m equals 1 into our original factorized form, we get 0 in both the numerator and denominator, which gives us an indeterminate form. When we encounter an indeterminate form, we need to go back to the original equation and substitute m equals 1 directly. Substituting m equals 1 into the original equation, 1 squared x minus 1 squared equals 3 times 1 times x minus 2 x minus 1. This simplifies to x minus 1 equals x minus 1, which is always true. This means that when m equals 1, any value of x is a solution, which makes the equation ambiguous. For m equals 1, the equation simplifies to an identity, meaning x times 0 equals 0. Any value of x satisfies this equation, because 0 times any number is 0. For m equals 2, let's go back to the original equation and substitute. 2 squared x minus 2 squared equals 3 times 2 times x minus 2 x minus 1. This simplifies to 4x minus 4 equals 6x minus 2x minus 1. Further simplification gives 4x minus 4 equals 4x minus 1, which leads to negative 4 equals negative 1, which is false. This means that when m equals 2, there is no solution to the equation. Today, we'll solve a problem involving a linear equation with parameters. Let's take a look at the problem. Let's look at this example. We have the equation 2ax minus b equals bx plus 3. We need to find for which values of parameters a and b the equation has infinitely many solutions. Step 1. Let's first rearrange the equation to get all terms with x on one side and all constant terms on the other side. We'll subtract bx from both sides. This gives us 2ax minus bx equals b plus 3. Now, let's factor out the x from the left side. We get x times the quantity 2 minus b equals b plus 3. Step 2. Now we need to determine when this equation would have infinitely many solutions. For a linear equation of the form coefficient times x equals constant to have infinitely many solutions, both the coefficient of x and the constant term must be 0. So our first condition is that 2a minus b must equal 0. And our second condition is that b plus 3 must equal 0. Step 3. Let's solve these two conditions to find the values of a and b. From our second condition, b plus 3 equals 0, we get b equals negative 3. Now let's substitute this value of b into our first condition, 2a minus b equals 0. We get 2a minus negative 3 equals 0, which simplifies to 2a plus 3 equals 0. Solving for a, we get 2a equals negative 3, and therefore a equals negative 3 halves, or negative 1.5. Today, we'll solve an algebraic equation by following a precise algorithm step by step. Let's consider the following equation. X plus m squared plus 2 equals m squared times x minus 3 times m. We need to find the values of m, for which this equation has infinitely many solutions. Let's start solving this step by step. Let's begin with our first step. We'll move all terms with x to the left side, and all other terms to the right side. So we subtract m squared x from both sides, and also subtract m squared and 2 from both sides. This gives us x minus m squared x equals negative 3 m minus m squared minus 2. For our second step, we'll rearrange this equation to standard form. We can factor out x from the left side of the equation. So this gives us x times the quantity 1 minus m squared equals negative 3m minus m squared minus 2. Now for our third step, we'll simplify the right side of our equation. We get x times the quantity 1 minus m squared equals m squared plus 3m plus 2, with the signs flipped. So our equation becomes x times the quantity 1 minus m squared equals negative m squared minus 3m minus 2. For our fourth step, let's simplify further by factoring the right side of the equation. We can factor m squared plus 3m plus 2 as the product of m plus 1 and m plus 2. So our equation becomes x times the quantity 1 minus m squared equals negative the product of m plus 1 and m plus 2. For our fifth step, we'll solve for x by dividing both sides by the quantity 1 minus m squared. This gives us x equals negative the product of m plus 1 and m plus 2 divided by 1 minus m squared. For our sixth step, we'll simplify the expression further. Note that 1 minus m squared can be factored as the product of 1 minus m and 1 plus m. So we have x equals negative the product of m plus 1 and m plus 2 divided by the product of 1 minus m and 1 plus m. For our seventh step, let's simplify the fraction further. We can rewrite this as x equals negative the product of m plus 1 and m plus 2 divided by the product of 1 minus m and m plus 1. Notice that m plus 1 appears in both the numerator and denominator, so we can simplify. This gives us x equals negative m plus 2 divided by 1 minus m. If m equals negative 1, our equation becomes x plus negative 1 squared plus 2 equals negative 1 squared times x minus 3 times negative 1. This simplifies to x plus 1 plus 2 equals x plus 3. Further simplifying, x plus 3 equals x plus 3. This is a true statement for any value of x. This means when m equals negative 1, the equation has infinitely many solutions. So our final answer is the equation has infinitely many solutions when m equals negative 1. Today we're going to solve an equation with a parameter. We'll find the values of m, for which the equation has infinitely many solutions. Let's look at our example. We need to find the values of parameter m, for which the equation m squared x minus m equals 4x plus 2 has infinitely many solutions. To solve this problem, we'll follow a step-by-step approach. First, let's rearrange the equation to standard form by moving all terms with x to the left side, and all terms without x to the right side. Now, we'll factor out x from the left side of the equation. This gives us x times m squared minus 4 equals m plus 2. Now, we'll factor m squared minus 4 into m minus 2 times m plus 2. This gives us x times the product of m minus 2, and m plus 2 equals m plus 2. For our next step, we'll divide both sides of the equation by m plus 2. This gives us x times m minus 2 equals 1. Notice that this division is only valid when m plus 2 is not equal to 0, or in other words, when m is not equal to negative 2. Now, we need to determine when this equation has infinitely many solutions. For a linear equation like this to have infinitely many solutions, both the coefficient of x and the constant term must be 0. In our original equation, after rearrangement, we had x times m squared minus 4 equals m plus 2. For this to have infinitely many solutions, we need m squared minus 4 to equal 0 and m plus 2 to equal 0. Let's solve these conditions. If m squared minus 4 equals 0, then m equals plus or minus 2. If m plus 2 equals 0, then m equals negative 2. So, the value of m that satisfies both conditions is m equals negative 2. Let's verify our solution by checking if m equals negative 2 makes the original equation have infinitely many solutions. When m equals negative 2, the left side of our original equation becomes negative 2 squared times x minus negative 2, which is 4x plus 2. The right side is 4x plus 2. Since both sides are equal for any value of x, the equation has infinitely many solutions when m equals negative 2. We've successfully found that m equals negative 2 is the value for which the original equation has infinitely many solutions. Let's summarize what we've learned. We started with the equation m squared x minus m equals 4x plus 2. We rearranged it to get all terms with x on the left side. We factored out x, and then factored the coefficient m squared minus 4. We analyzed when the equation would have infinitely many solutions, which required both the coefficient of x and the constant term to be 0. We found that m equals negative 2 is the only value that makes the equation have infinitely many solutions, and we verified this by substituting back into the original equation. This example demonstrates how to work with equations containing parameters and how to determine special values of those parameters that give the equation particular properties. Today, we're going to solve an equation and determine for what value of the equation has no solution. Let's look at our example. We have the equation a squared x plus 3 equals 9x plus a. We need to find for what value of this equation has no solution. Let's solve this step by step. First, we'll rearrange the equation to get all terms with x on one side and all other terms on the other side. We start with our equation. A squared x plus 3 equals 9x plus a. We'll move all terms with x to the left side and all other terms to the right side. This gives us a squared x minus 9, x equals a minus 3. Next, we'll factor out x from the left side of the equation. This gives us x times the quantity a squared minus 9 equals a minus 3. Now, we can solve for x by dividing both sides by a squared minus 9. This gives us x equals the fraction a minus 3 over a squared minus 9. Let's now factorize the denominator. We know that a squared minus 9 can be written as a minus 3 times a plus 3. So our expression for x becomes a minus 3 over the quantity a minus 3 times a plus 3. We can simplify this fraction by canceling out the common factor a minus 3 in the numerator and denominator. This gives us x equals 1 over a plus 3. Now, when would this equation have no solution? A fraction has no solution when its denominator is equal to 0. In our case, that happens when a plus 3 equals 0, which means when it equals negative 3. However, we need to be careful here. We need to check the conditions under which our simplification is valid. Our simplification assumed that a minus 3 is not equal to 0, which means it is not equal to 3. Let's check what happens when it equals 3. If we substitute a equals 3 into our original equation, we get 9x plus 3 equals 9x plus 3, which is true for any value of x. This means when it equals 3, the equation has infinitely many solutions, not no solutions. Now, let's check what happens when it equals negative 3. If we substitute a equals negative 3 into our original equation, we get 9x plus 3 equals 9x minus 3, which simplifies to 0 equals negative 6. This is a contradiction, which means when it equals negative 3, the equation has no solution. Therefore, the value of a for which the equation has no solution is a equals negative 3. Today, we're going to solve two linear equations step by step, following a precise solution approach. Let's look at our first example. We have the equation a minus b times x plus a minus 1 equals 0. We need to determine for what values of a and b the equation has infinitely many solutions. Let's begin solving this problem. To have infinitely many solutions, we need to rearrange the equation to isolate x first. Now, we solve for x by dividing both sides by a minus b. For the equation to have infinitely many solutions, we need to consider two cases. First, if a minus b equals 0, then a equals b. In this case, the coefficient of x is 0, making the equation independent of x. In this case, for the equation to be valid, we need a minus 1 equals 0, which means it equals 1. This gives us our first solution, a equals b equals 1. Let's also consider the second case. If 1 minus a equals 0, then a equals 1. This makes the numerator 0, which means the equation becomes x equals 0 divided by a minus b. For this to give infinitely many solutions, the denominator a minus b must also be 0, which again gives us a equals b. Therefore, combining our findings, the equation has infinitely many solutions when a equals b equals 1. Let's move on to our second example. We have the equation m minus 2 times x minus 2m equals 3x minus 10. We need to solve this equation for x when m is not equal to 5. Let's begin solving this problem. First, we'll rearrange the equation to collect all terms with x on the left side and all other terms on the right side. Next, we factor out x from the left side of the equation. Let's simplify the expression inside the brackets. Now, we can solve for x by dividing both sides by m minus 5. Remember, we're told that m is not equal to 5, so this division is valid. Let's simplify the right side by factoring the numerator. Finally, we can simplify this fraction, since m is not equal to 5, by canceling out the common factor m minus 5. Therefore, the solution to our equation, when m is not equal to 5, is x equals 2. Today, we'll solve a quadratic equation problem, where we need to find the value of m, for which x equals -1 is a solution to the given equation. Let's start with our example. We have the equation mx cubed minus open parenthesis 2m minus 1 close parenthesis x equals 5. We need to determine the value of m such that x equals -1 is a solution to this equation. To solve this problem, we need to understand what it means for x equals -1 to be a solution of the given equation. A value of x is a solution to an equation if, when we substitute that value into the equation becomes true. So let's follow the steps to solve this problem. Step 1. We'll substitute x equals -1 into the original equation. This gives us m times -1 cubed minus open parenthesis 2m minus 1 close parenthesis times -1 equals 5. Step 2. Let's simplify the left side of the equation. First, -1 cubed equals -1. So, m times -1 equals -m. Next, -1 times open parenthesis 2m minus 1 close parenthesis. When we distribute the -1, we get -2m plus 1. Step 3. Now, let's substitute these values back into our equation. We have -m minus open parenthesis -2m plus 1 close parenthesis equals 5. Simplifying, we get -m plus 2m minus 1 equals 5. Step 4. Let's simplify further and solve for m. Combining like terms, we get m minus 1 equals 5. Adding 1 to both sides, we get m equals 6. Let's verify our answer by substituting m equals 6 and x equals -1 back into the original equation. We have 6 times -1 cubed minus open parenthesis 2 times 6 minus 1 close parenthesis times -1 equals 5. This gives us -6 minus open parenthesis 12 minus 1 close parenthesis times -1 equals 5. This simplifies to -6 minus 11 times -1 equals 5. So, -6 plus 11 equals 5. And finally, 5 equals 5, which is true. This confirms that m equals 6 is the correct solution. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.